Hey everybody, this is the analytical video for the lunar observations I did on April 28th and 29th, 2018, that night. What you're seeing here are just the moon photos that I took that got the filter flare on them, and as you can see, the actual moon in all these photos is overexposed. If it was in focus, you wouldn't get it. But I just want to say a couple things here before we get started. First of all, I am not going to get into the detailed math on this. I've already done that before. That will all be at the end. The Dial-A-Moon excerpts will all be at the end, but remember, Dial-A-Moon is in UTC. I converted everything here to Central Daylight Time, even if it was UTC, just for consistency, but the Dial-A-Moon is in UTC, and at the very end you will also see the mooncalc.org slides for the actual measurements that I took and the times. Well, to the closest minute. You can't get seconds with that. But anyway, all right, that's just the intro, and let's get started on this here. Okay, first what we're going to do is we are going to take the raw photo with all the information here from each of the 5 observations. O1 is observation 1, O2 is observation 2, etc., all the way to 5. Remember, I did 5. I took a ton of photos during these time periods, but I selected the one that I thought was best where I could see the most stuff. So you're going to see all the information here on the left. Now what I've done here is, here you see the photo I selected. I cropped it, pulled up the contrast, or adjusted the brightness, whatever I had to do to be able to see it better. And in the entire video, every photo was taken with a leveled tripod, the best that I could. Anytime you see a yellow dot with a red circle around it, like you do here, that is going to be Tycho crater. That holds true throughout this entire video. All right, now in this one here, I put the closest Dial-A-Moon. Remember, I converted all the Dial-A-Moons to Central Daylight Time, but I put the UST -5 here, so you know to add 5 hours when you go to Dial-A-Moon. Now here, what I'm showing is that the moon, the Dial-A-Moon, in order to get it how it appears to me in the sky, I have to rotate it. All right, because Dial-A-Moon is oriented as if you were looking straight up on it from like the North Pole, so you could see, you know, its orientation relative to the ecliptic. But I am at a latitude, so that changes. All right, so Tycho's going to appear rotated. This is the only observation you're going to see where I have done that. All right, so then I take the observation and I get my angle from Tycho crater. I'm doing this all in the bottom half because that's where Tycho crater is, hence the horizontal line. The vertical line is just my y-axis. It's my base to get my angle. All right, that's all that is. And here I physically measured it. It came out to be 51 degrees. Now I take the closest Dial-A-Moon. Now I keep it in its original position here. All right, and I figure out where Tycho crater is here, and here I get a 2.5 degree angle, and they're both in the same quadrant here, the southeast. So in order to get my actual sway, I have to subtract the 2, and in that case I get 48.5 degrees, which is my complementary angle to my latitude, in this case 41.5 degrees. All right, so which we predicted in previous videos that when the moon is near the horizon, I should be able to get my latitude via the complementary angle. All right, okay, so here is photo 2 unaltered. There's all the information on it. All right, here is the moon altered and cropped so you can see Tycho crater. Here's my angle. I get 39 degrees. There's my Dial-A-Moon for the closest time period. Remember, Dial-A-Moon's only in even hour increments, so I have to go with the closest one. Libration was present here, but it was off by about, I think it was total maybe 3 degrees, so it wasn't anything drastic to affect any of my measurements, really. All right, so I then do the same thing I did in observation 1. I do the Dial-A-Moon thing, I figure out my complementary angle, and I get 53.5 degrees. Now this is going to come up again, and you're going to see this observation is the only one that doesn't fit my predictions. All right, so let's just get through these. Okay, here's observation 3, raw photo, and now we're in the full phase because the moon did go from a waxing gibbous to a full phase this night. So there's the moon as it appeared to me in the sky, and as you can see, Tycho crater, 2 degrees. Now, it doesn't look that different from the Dial-A-Moon, does it? So the Dial-A-Moon is the same thing, which I shot this photo at moon, what I call moon noon. or lunar midnight in this case since it's dark out, which is the high, what is that called? Not complementary. No, I can't think of it right now. Well, I call it high noon, and I explained in another video why I did that. If you'll see words come across the screen if I correct. Oh, culmination. It's high culmination. Sorry. The reason why I use high noon or moon noon instead of culmination is because there are actually two culminations. There's a low and a high, but I've explained that before, and I'm sorry I stumbled. All right, here's the next observation. Raw photo. There's the cropped and altered one, so I could see Tycho. There's Tycho marked. I get 25.5 degrees. There's my dial-a-moon. Now, my 25.5 degrees on mine is in the southwest quadrant, but here in the dial-a-moon photo, it's still in the southeast, so I have to add my two angles, and then I figure out my complementary angle, which in this case is 63 degrees. All right, here's the final one that I decided to use. It was getting near moon set. As you can see in the distance, I'm getting things like vegetation in the way. So here's my altered one. I actually did not alter the color on this. I just messed with the contrast and the brightness and I think the sharpness, and it turned it that color. But anyway, here I do the same thing as I did with the other observations. I get 47 degrees. There's my dial-a-moon for the nearest time. I do that, and I only get half a degree, so my complementary angle to 47.5 degrees, because I have to add that 0.5 because they're in different hemispheres, is 42.5 degrees. That's close to my latitude of 41.5. It's off by a degree. When the moon's near the horizon like this is actually hard to do, because the moon, as it starts to set, you start to get the atmospheric interference because the light has to go through more atmosphere. And although the angular size of the moon doesn't change, if it's hazy, it can mess with your picture, and I'm in Northwest Indiana, so it's always hazy here. All right, so that concludes the 5 observations. Now what we're going to do here in a second, I am going to take my 5 observation photos with the Tycho crater highlighted. I'm going to overlap them to see if they fit my model of the predicted sway throughout the night. Remember, all the math is at the end. I'm not going to go through the math in detail here. Okay, so here's our observation 1. I put my observation 2 over it, increase the transparency so I can see where Tychos are. I do this for 3, I do this for 4, and I do this for 5. Okay, now I'm going to put my circle over the moons, the best fit that I can. Okay, now I'm going to drop the moons. All right, so now I'm comparing the sway at Tycho crater to all 5 observations to the maximum predicted swing of 97 degrees, and that 97 degrees is the sum of the 2 complementary angles, 48.5. That gives you 97, all right? And there's the Tycho dots throughout the night, okay? Here's my 5 observations where Tycho is relative to each of those observations, all right? Now here's the observed angles for those observations. Okay, once I took the dial-a-moon into account. All right, and I put negatives by the ones in the southwest corner, but I mean, it doesn't really matter. All right, now my predicted angles for the observations compared to the actual angles. Now throughout the night, I made predictions. You know, I tried to divide the night into 4 equal parts. All right, so then I would take each of my observation at each one of those points, and I would calculate a predicted angle. And as you can see, the predicted angles are in blue, the observed are in white. As you can see, they're all pretty close, except for O2. I don't know why that is. The white circle there is just to show you, is like a second point, you know, how Tycho would spin as it appears across the disk of the moon. Now, as you look up in the sky, this parallactic angle, or this sway, is caused by, you know, the Earth rotating, all right, relative to the moon in the sky from my vantage point. So I should be able to predict all these angles. Now it's not exact because I'm using a circular conic section to predict this. It's a little more complicated than that. I understand that, but I should still be close. Here's my error calculations. O1 is just 3.5%, O2's 13.5%, 1.6%. Even in my model, I should not be that far off. My O3, I'm off less than 1%. My O4, 2.6. My O5, 1.5. My predicted margin of error based on previous lunar observations is plus or minus 4%. I think in another video I said plus or minus 5 or plus or minus 2 to 5. Well, I actually calculated it. It's closer to 4. And as you can see, every one of these is within that tolerance except for O2. Well, why is that? Honestly, I have no idea. There's a couple of possibilities, really. Okay. Now, if I would have known I was going to have one that was so out of whack like this, I would have done it every hour. All right, but I did need some sleep. But I do have 4 data points out of the 5 that conform really well to my predictive model. So O2 is either an outlier, all right, that is an outlier because I screwed up. My tripod either wasn't leveled or there's some part of this equation that I am not taking into account. Now, if my tripod wasn't leveled, Tycho's still going to fit along that white circle. It's just going to be off by more than the predicted angle, which is exactly what happened. And if there is something in this equation I'm not taking into account, I don't know what that is. If any of you know, please feel free to let me know. I would be happy to know what that is. Okay, now we're going to have a little fun here. What you're seeing here is each of the 5 closest dilamoons to my observations. And as you can see Tycho craters swaying slightly, but you can, if you look in the lower right or lower left-hand corner of the moon, you can also see the phase of the moon increasing. Well, does this happen in my observations? Well, I took observation 2 and observation 4 here, put them side by side. O4 was rotated 63.5 degrees. That's the sum of the 2 angles of the swing of Tycho crater to line up with O2. Okay, so I positioned O4 relative to O2. Now, the arrows are pointing to the waxing side of the moon, that lower left from my O2 vantage point. Now, we go to mooncalc.org, we get 98.8% full for the O2 observation and 99.3% full for the O4. Well, do we actually see this? We'll keep watching, Laura. Here's O2. I'm going to mark some of the craters for you. And look at the horizon. And look how you can see the shadows and craters. There's O2. Here's O4. It has changed. All right. Not only has it become more full, as you can see, but you can see the moon, this Tycho crater has swayed in a different position relative to 4, because not only is the moon becoming more full, but we're getting daily libration. I've talked about libration before. The parallactic angle or swing of the moon that we see throughout the night with Tycho crater shifting is not libration. Libration is by definition us being able to see more of the moon's surface over a period of time, either daily or from night to night, or weekly, or monthly, or yearly, whatever. That allows us to see over the course of the year 59% of the face of the moon instead of just the half from the one side facing us. All right, so now we're going to zoom in on O2 and just look here. Here you can see some of the features, and now we're just going to compare that with O4. And as you can see more of the craters that were not visible before, and it kind of shifts up. That shift up is daily libration. The seeing more of the moon is just the phase increase during the night. So I just thought that was really cool and that I would show you all that. All right. Okay, I hope I didn't blow through that too fast, but as promised, here are the mooncalc.org slides. Here is my math, and here is going to be the dilamoon for each of the closest observations as promised. But if you have any questions, comments, or you can answer any of my questions, please feel free to leave them below. But anyway, that's it. And good news, this is the last lunar video for a while, like I said before, unless there's an ISS transit we need to catch or something. But anyway, that's it, and it's time to start the geology field season.